Okay, so welcome everyone to the University of Washington's database seminar. And this quarter we will discuss about Bitcoin and blockchain technology and how all this relates to data management and databases. And the first lecture will be given by Shumo Chu, who is a fifth-year graduate student in our group.
Great, thanks, Dan. So first, welcome to the 590Q, and this is the hashtag of the Slack channel. If you are Allen School students, please join us in this channel. And this is a mail list we created. And if you are like sort of outside Allen School, you can join this mail list and get all the announcement. So first, I will try to, although I don't think we need much motivation, but I still try to motivate this, the theme of this seminar. So the goal of this seminar is really we're trying to understand the blockchains and cryptocurrencies. So we want to do a deep dive into the technology first, and then we are explore various potential research topics, including how to scale up blockchain transactions, how do people think of smart contract application which run on blockchains, and the architectural support, and many others. Well, I want to be explicit here. One of our non-goals is not help you make money by doing investment on those cryptocurrencies, although you might be able to after you learn this technology. And a famous database researcher, Mohan, give a colloquium talk like several weeks earlier. And his main point is that like we really need to separate Bitcoin and blockchain. And he is sort of promoting the private chain. And I would say for famous database researcher, as smart as he is, I almost disagree with him in every aspect. So I think the blockchain and Bitcoin, they are tightly collected, and you will see, especially when we are talking about smart contracts. And I don't think the private chain is the future of the blockchain. But this is only my personal opinion, I want to say here. So first, for this seminar, we have a bunch of external speakers and invited speakers from Allen School. And those are 3 remaining slots that open for sign up. So the first one, so basically, we try to organize this seminar within certain theme. And the first one is January 23rd. We'll be talking about smart contract, especially like the Solidity, the programming language for smart contract, and the Ethereum virtual machines of the runtime of the smart contract. So and then January 30th, we'll talk about scalability and performance. 2 of these potential papers we could discuss about is Algorand from SOSP this year and a Blockbench from Sigma this year. And for the February 20th, we'll talk about security and verification. So, each presenter need to sign a videotaping agreement here because we want to share this seminar video with others. So anyone want to sign up right now for this? So okay, Dylan, which one would you want to go?
I'll take the smart contracts for 500.
Great. So how about the scalability and performance? I think in theory, like every people who signed the seminar need to give a presentation here. And
I'd be happy to have a partner too.
Yeah, of course. Okay, Kong, you will do the January 30th. Great. And how about the security and verification? I could do that. Great. Okay, I'm happy to talk to you guys offline. So for today's talk, I'm going to first cover necessary crypto background to the Bitcoin and blockchains. So more specifically, we'll talk about hash functions. And these are like crypto hash functions and related data structures and digital signatures. And after we cover all the crypto background, we'll go to talk about an intro to cryptocurrencies. And literally, we'll talk about a very fundamental design of basic digital cash system. And then if we have time, we'll talk about a bit more about history and of the cryptocurrencies and Bitcoin. And really thank Arvin from Princeton for providing the slide. This is basics. This is as a basis of these slides. So let's first talk about crypto hash functions. So first, let's forget about crypto. What is a hash function? So hash function has these three properties. First, it can take any size of string as input, and you basically can view anything as a string. And second, it outputs a fixed size output. So here we would assume it's 256 bits. And third, it must be efficiently computable. And in addition to these hash function properties, crypto hash functions has three more properties, which we will cover one by one. The first is collision-free or collision-resilient, and the second is hiding, and the third is puzzle-friendly. So let's first look at the first sort of crypto properties of the crypto hash functions. So first is collision-free. Essentially, this is that like nobody can find x, y such that x doesn't equal to y, and they have the same hash result, right? You might want to ask, is that possible? Because collision do exist. One simple argument is that because a hash function takes a string with the arbitrary size, the space of possible input is much larger than the possible output. But here we're not arguing that collision doesn't exist. We're arguing that can anyone find them? Because the hash function, the input space is much larger than the output space, we can see that anyone can find them simply using the counting argument. A well-known theme here called a birthday paradox. So basically, essentially for any hash functions of output size 256 bits, you just try like 2 power 130 random trials. You have a very large probability to find like hash collisions. Like this is simply the math. Well, this works no matter which kind of hash function it is. But the problem here, you can say that the number of trials we want in order to find that is actually a super large number. And basically, it's impossible, impractical if we really want to use this method or try to find the hash collision. Well, then a natural question to ask is that, is there a faster way to find hash collisions? Well, the fact is here, for some particular hash functions, yes, right? One easy example is that if you just use a hash function of you treat the string as a number, and you do the modulo over a prime number, let's say. As long as you know the prime number is, you can very easily find hash collisions. There is no secret here. Well, as a matter of fact, in fact, there is no hash function has ever been formally proven to be collision-free. Although people really want to try to prove that for a bunch of hash functions, but there is simply no proof yet. So the best thing we can say here is that there is a certain kind of hash functions, a lot of hackers and crypto researchers trying to find efficient method to break these hash functions for many, many years, and no one have succeeded yet. So people generally believe that this specific kind of hash function is practically collision-free. So that's which kind of guarantee we have here. So let's look at an example of this collision-free, why we need a hash function to be collision-free. So the application here we call a message digest. So because the hash function is essentially collision-free, if we know that the hash of two results are the same, so it's kind of safe to assume that the original input to the hash function are the same. Well, this can be used, for example, if you want to recognize a file that we stored before, we don't need to store the entire file. We just need to remember its hash. And it's useful because the hash is usually much smaller than the file itself. That's about the collision-free property. So let's talk about the second property of crypto hash function, which is hiding. So for hiding, we want something like this. Given the hash of x, it's infeasible to reverse and find the input to the hash function. You might say, what if the hash function's input is super simple? For example, what if the hash function's input only have two possible inputs, which is the result of the coin tossing, either head or tails? What do we do with that, right? So basically, if you just compute the value of a hash function of these all possible inputs and store them, you basically know like which kind of, you basically can reverse engineer what the input is. Well, so here is the solution for these problems. So more formally, the hiding property is defined is that if we have some sort of random seed R, this random variable is choosing from a probability distribution that has high min-entropy. Then we actually can, for the input, we concatenate the original input x with this random variable, and we compute its output. Then it's infeasible to find the original x in this context. Well, the high min-entropy in information theory actually means that the distribution is very spread out, and which means there is no particular value to chosen with more than significant probability. So that's about the hiding property. And what's the usage of the hiding property? One possible application here is we call it commitment. So intuitively, you can think of a commitment as something like if you want to sell a value in the envelope, and people can see the envelope, but by the time you sell the envelope, nobody can see the value. And in a later period, if you decide to open the envelope, then people know the value, and also people know that this is the value exactly you put in the envelope before you sell the envelope. So this is we call a committed value, and review it later. Well, that's sort of the API of doing this commitment. So we have a function called commit. Take a message itself and a key. It will produce a commitment message. And later we can verify the commitment message by reviewing the key, the message, and the commitment message. So here if so the analog here is that if you sell a message in the envelope, basically you call the commit method and then publish the committed message. And to open envelope, the original committer need to review the key, and anyone else can check the validity of this commitment. Well, here we're really using the you can obviously infer that this commit method, which is the key technology here, and this is using the property of the hash functions. Because we have the hiding property of the hash function, so at the time of the commitment, given the committed message, it's infeasible to find the original message, right? Also, we have the binding property, which means binding property is used to verify the validity of the commitment. So intuitively, this means it is infeasible to find another pair of message and key, let's call it MSG prime and key prime, such that the committed message is the same. So basically, there is no one else practically can sort of get a fake message, get a fake commitment for you. So that's about the second property. And let's look at the third property. We call it puzzle friendly. And for this property, it's a little bit trickier. So puzzle friendly property said, for every possible input value y, let's assume it has n bits. If there is a key that is chosen from a distribution, again, with a high min-entropy, then that is infeasible to find x such that the hash of the concatenate of k and x equals to y. You may want to say what's the difference in the hiding property, right? So we'll reveal later. And here, more specifically, we we actually requires that the time to reverse engineering this hash function must be no less than 2 power n. Well, n is a size of output of this hash function. Well, to better understand what's a puzzle-friendly property, let's look at the application here, which is a search puzzle. So here we are given a puzzle ID. Again, this is from a high min-entropy distribution, and the target set of y. So basically, y is a set of values, and we actually requires that this set of value is much smaller than the space of all possible outputs, but still can contain many values. And here we really want to try to find a solution here, solution x, such that if you hash the ID and x together, the hash result is within the set of y. So this is called a puzzle-friendly property. And this puzzle-friendly property basically implies that there is no efficient solving strategy that is much better than just trying to do random guess. And this is extremely useful in the second talk here, talking about the decentralization. But practically, the most hash functions can only take an input with a fixed size. So how can we solve that? So it turns out there is a very nice scheme to solve that, which is called a Merkle Damgard transformation. So basically, we don't need any hash function that can take a arbitrary size of input. So here, what we need is a hash function c, which takes a fixed input. So let's see the hash function c here takes 768 bits and output 256 bits. So what we do here is that, so first we have a seed, and this is just like a random seed you will choose and you will remember, which is 256 bits. And then we divide all the input to this hash function to blocks with 512 bits. So first, we concatenate the seed and the first block, and we call the hash function. And remember, the output of this hash function is 256 bits. Then we just do it again and again until we reach the final blocks. And the end result of the last call of this basic hash function is the end result. And people have proved that the theorem that if the basic hash function c here has all the crypto properties we just stated, then the entire application of this series of a hash function, if you think the entire scheme as a single hash function, and this hash function also have the same crypto properties. So that's a so we just did a review of the hash functions. Any question here? Okay, so since we have to talk about hash functions, how people can actually use these hash functions in blockchains and bitcoins, and the most useful places for these hash functions is we actually build data structures. And first, let's talk about hash pointer, because hash pointer is a basic thing for many different data structures. So essentially, a hash pointer is a regular pointer, which is pointing to some information where the information is stored. In addition to this basic pointer, we also have the hash of this piece of information that this pointer is pointing to. So essentially, if we have a hash pointer, instead of just going back to the information, we can also verify that that piece of information hasn't been changed. So this is a really simple idea. So this is what a hash pointer looks like. So we have a piece of data, and we have a pointer, and we have the hash value stored in conjunction of this hash pointer that can be used to verify the validity of that piece of data. Well, this turned out to be a very powerful idea because we can build many kind of data structures with these hash pointers, and those data structures are super useful. So one most simple hash pointer-based data structure we call it blockchain, right? So basically, hash pointer, you can think of blockchain as a linked list, but using hash pointers. So more specifically, here you can say that we have a block of data, and we have the hash pointer pointing to that piece of data. And this is like easy to understand, right? So one specific thing I want to point out here is that you must ensure that, for example, this hash pointer that pointing to this piece of data contains a hash of the data and the hash pointer in conjunction with that piece of data. And this is a kind of essential to give us some nice properties of this hash pointer. And why this blockchain is useful, because this is essentially a tamper evident log. So what is tamper evident? Basically, by using this blockchain, no one can ever change this piece of data. Why is that true? So let's say if someone wants to change the data, right? So let's say if someone wants to change that piece of data, because the signature of that piece of data is actually stored with the hash pointer, and one needs to change that piece of data too, and so on. So, and essentially, the end hash pointer will store the hash of the last piece of the block. And because the hash pointer is very small, this piece of the end hash pointer is kept by the end user. And which means now the end user can very easy to verify that the entire blockchain has not been tampered. So that's the idea of a blockchain, or we can call it like hash pointer-based linked list. And similarly, we can build tree structures. So here the tree is named by a crypto researcher called Merkle, and essentially this is a hash pointer-based binary tree. So the idea here is that we store all piece of data in the leaf node. And for leaf node, we group the leaf node together by pairs. And for each pairs of the leaf node, we first compute their hash values, and we group their hash values as their parents. And if you want to grow up the tree, so we can see the upper level of it also contains the pairs, store the hash information of the pairs of the intermediate node. And why this is useful? Because think of if you want to prove that certain piece of data is indeed a member of this Merkle tree, now you only need to show log n items, which essentially you only need to show the hash node that's from the root along to the path of that piece of data. And because that's only log n items, it's usually this piece of data can be stored very efficiently. So you might ask, Dylan.
How do you actually go down the tree and determine whether a data is looked up? Like, what do you use to as comparisons at each level of the tree? Do you use the data itself or a hash of it?
So the question is, how do you look up the data, right? So I think I'm not particularly clear about that point, but I think essentially there are some like auxiliary information you can store, and this auxiliary information can be hashed as well. I don't think there is a fundamental difficulties of doing that.
Okay, so there might be an auxiliary data structure that's a regular binary tree.
Yeah.
So the hash pointer is a combination of both the regular pointer and the hash of the previous data that it is pointing to. So you actually have the pointer to. It's not a separate data structure.
Okay, so we would just do normal binary tree lookup on the
Yes, in addition you have the hash so that you can ensure the tampering property.
Yeah. So one thing we can compare here is that, so I mean, theoretically you can use a blockchain to check the membership, right? But the real benefit here is that instead of you need to traverse every piece of data in the blockchain, now you only need to have a log and lookup, right? Like we said, so this tree can hold many items, and a user wants to verify the validity of data, only need to remember the root hash. And again, if anything is tampered, the root hash have to be changed, right? So there is also a variant of the Merkle tree, which is called the sorted Merkle tree. So sorted Merkle tree basically still a Merkle tree, but there is an invariant that the end piece of data, which is at the bottom of the tree, must be sorted with the order you want. So the particular property of this sorted Merkle tree is that instead of, in addition to verify the membership, now you can verify non-membership. Essentially, to verify the non-membership, you just need to provide the proof that there is a two adjacent data block before, sort of at the range before the non-membership you want to look up, and after the non-membership lookup. You just need to provide the two pieces of membership proofs. Then this becomes a non-membership proof. And more generally, these ideas of using hash pointers can be applied to any pointer-based data structures with no cycles. And that's for obvious reason. If you have cycles, how do you compute the hash? You can never be successful. And we have reviewed the hash functions and hash pointer-based data structures. Now we're talking about another crypto primitive, which is digital signatures. I know as a computer science audience, for many of you, we still know, you already know that. But we want to still review that so that that's better help us to understand the future lectures. So first, a digital signature is kind of analog to the real-world signatures. And what do we want from real-world signatures? So the property you want from the real-world signatures is that we actually have two properties, right? First, only you can sign, and anyone else can verify that you sign. And secondly, second property is also important, is that your signature is tied to a particular document. Others cannot cut and paste your signature to other document. So this is really like the analog of the digital, like which kind of properties we want from signatures. And for digital signatures, we also have the similar properties. So for digital signatures, first we have a function called generate key. Basically, it takes a key size as the input, and it generates a secret key and a public key pair. For the secret key, you must keep it secret by yourself, and the public key is public accessible for anyone else. And then you can use this pair of keys to sign document. You can sign a message only using your secret key. And after you sign the message, you will generate a signature. And for the signature, anyone else can verify the validity of this signature using the public key that is public, of course, the message itself that you reviewed, and the signature itself. So basically, others can really check it's indeed you who has a secret key signed this signature. So, as an analog to the real-world signature, so we want the dictionary signature. First, we can verify that, and second, and more importantly, no one else can forge your signatures. So we can think of this as a security game. So here is you have the secret key and public key pair, and there is an adversary who knows the primary key. Sorry, not the primary key. I'm a database people really. Who knows the public key and get to see a few signatures on some message you have signed before. This is inevitable, and we want to make sure that this adversary cannot produce a verifiable signature for any message he wants, right? So let's try to play the game. So here we have a challenger and an attacker, and some of you might know who he is. Anyone know who he is? He's a Julian Assange.
Oh.
Never mind. So, so let's say we have a secret key and public key pair, right? So of course the challenger knows the secret key and public key both, while the attacker only knows the public key. So here we actually make the game a little bit more easier to the attacker. So basically, attacker can use any kind of method, maybe even social engineering, to send a message to the challenger and ask the challenger to sign. And this attacker can send many, many messages. As long as the number of messages is much smaller than the possible, all possible output, that's fine. Then eventually, we want to ask the attacker to sign a message. Well, this message is not in any of these previous message that the attacker let the challenger sign. And basically, we want him to fake this signature without knowing the secret key. So if true, then the attacker wins. So this is for the crypto hash functions. For the digital signature algorithms, actually they must guarantee this. And in terms of number of messages that an attacker can ask the challenger to sign, it could be in the magnitude of millions actually, because that's in some cases you will have that many transactions. So for the time's sake, we'll not discuss the details of these how these algorithms work, but there are some practical stuff that's essential and we should know. So first, the algorithm must be randomized, like fully randomized. So we need a very good source of randomness. So for example, when you are generating the secret key and public key pair, you need a really good source of randomness. If that cannot be guaranteed, there is no known algorithm can guarantee that your signature is not leaking information. That's the first thing. And second, although practically we have a limitation of the message size, but really, like we have talked before, you can use hash functions to solve this problem. And even funnier trick is that you can assign a hash pointer, which essentially you can assign like any size of data as possible. And as a particular digital signature algorithm that Bitcoin uses, this elliptic curve digital signature algorithms. For someone who is knowledgeable in security, this is not the digital signature algorithms that are used by most people today. And actually, Santoshi himself chose this signature. There is rumors that because RSA have secretly have a way to hack other kind of digital signature algorithms, but this is just rumors. So also, we'll skip the detail here. At the end of the day, what we really want to know is that for any kind of this digital signature algorithm, what we really want is we must have a good randomness. So next, we'll talk about we have just talked about another crypto primitives digital signatures, and now we're talking about one of the very important aspect of Bitcoin, which is public key as identities. So here, for any transactions in the Bitcoin or blockchain world, there is no such thing called a real identity. So essentially, every identity is just a public key. And why we can do that is if you see a signature that and you can verify it using the public key, that's equivalent as someone has someone has a secret key and public key pair set, this message being signed. And the reason is that to speak for this particular public key, you must have the secret key. And so since now the public key becomes the identity itself, then creating a new identity is really easy, right? So you just need to generate a new random key value pair. Sorry, not key value pair. Generate a new random secret key and public key pair. And the only way you can control the identity is you own the secret key. And here, if the public key looks purely random, no one can guess the information of who you are purely from the public key. Well, this is really sort of like a decentralized identity management. First, any people can make new identities at any time they want. And secondly, there is no central point of coordination. There is no some third-party identities can verify and decide like who you are and verify your credentials. So here, in Bitcoin jargon, these identities called addresses. And you might want to say from a privacy point of view that it really has a kind of strong privacy guarantees because addresses is not directly connected to the real-world identity. But in fact, it is not, right? Because observers can link together address, activity over time, because at the end of the day, you still need to do something using this address. And people can link can trace back the address, and the other address, this address interact with, make some inferences, right? So this is I think this will be a interesting topic itself for the privacy in blockchain area. And also, as a matter of fact, if you're following the newest policies, if you're doing some trading in the Coinbase or GDEX, so any trading that exceed a certain threshold, the Bitcoin exchange need to report to IRS. So there are some enforcement from the real world to try to regulate this space as well. So we have a talk about the crypto primitives. We talk about one key aspect, which is public key as identities. Now let's see how can we build a really simple cryptocurrency. Let's call this. Oh, first, any questions for the previous section? Great. So let's call this new cryptocurrency we built GoofyCoin, right? And to create a new cryptocurrencies, the first rule is how to create new coins. And here is really simple. You just have a unique coin ID, and you have a message called a create coin. And this message must be signed by the creator of a coin, let's say Goofy, right? And this can be verified using the public key of Goofy. And secondly, we need to know how to spend the coin. So the rule here is that we need for the transactions of spending the coins, we need to link this transaction with the previous transaction that create the coin. And only the owner of the coin who can spend it, which means for the coin that Goofy just created, only himself can spend it. And let's say the way he spent it is to pay the coin to Alex. Then what he really need to say is in the message that pay this coin to Alex with a certain amount and sign the new transaction of spending the coin. And now Alex owns the coin, right? So also the recipient of this coin now has the ownership of the coin, and Alex now can, for example, pass on coin to Bob as well, right? Everyone looks good, except if Alex is a malicious people, and now she has the ownership of the coin, she can at the same time send the coin to Bob and Chuck, right? No one is preventing her from doing that in the current system. So, and this is called double spending attack. And this is actually the main challenge of designing digital currencies. We must have a way to prevent this double spending attack. And so now we try to think hard again and try to design a new coin. Let's call the new coin Scrooge coin. So if you think of how to preventing double spending attack, so really we must have some consensus to be made on the ownership of the coin, right? And a specific coin cannot be owned by two parties at the same time. So one possible way is, so now let's say Scrooge is the creator of the coin. And also, another job of Scrooge now is also he needs to maintain the history of all transactions. And all transactions is not valid unless this transaction is signed by Scrooge. And by that way, as long as we assume that Scrooge is an honest person, then, for example, the malicious users, for example, Alice, cannot tamper the coin. So here, of course, Scrooge maintain the blockchain data structure, as we have introduced before. And normally for performance purpose, people usually put multiple transactions in the same block. This is kind of like a batching of the transactions. And because Scrooge himself is still using the blockchain data structures, as we know before, although there are some certain kind of behaviors that Scrooge can do, we can still sort of have some guarantees at least. For example, once Scrooge publishes these transactions, it's immutable, right? Even Scrooge himself cannot change the transaction anymore. And also this can be verified by purely just keeping the hash pointer of this blockchain. So let's take a detailed look of how can Scrooge do the create transactions. So the first kind of transactions is to create coins. So let's say this transaction has a transaction ID, and a type of transaction is create coins. And Scrooge now can create different kind of coins, which each creation has a number of coins, and basically this is the ID of the coin, and the value of the coin, and the recipient of the coin. So so basically we have a unique identifier for each single coin. So this is a create coin block. And in order this transaction need to be valid until Scrooge himself sign this block. And now we look at second kind of transaction block, which is a payment block or consume block. So basically, the key idea here is that this payment or consume block will actually destroy some coins and create new coins of the same total value. So, for example, for this specific block, it consumes several coins and creates some new coins, and it requires a bunch of signatures. So for these create coin blocks, we have some actual requirements. So those are 4 requirements we required, and let's go through them one by one because this is really important. First, this consume coin block requires that the consumed coin, which is the source of this block, need to be valid and not already have been consumed. And these two properties can be checked using the blockchain properties, as we have introduced before. And also, we want to requires that the total number in, which means the total amount of value of the coins that are being destroyed, equals to total value out, which is the newly created coins. And also, we need these transactions signed by owners of all the consumed or destroyed coins. So this is like a four important invariants this consumed block requires. And this consumed block is not valid by the semantics of the transaction if any of them is violated. So now we can see that an important properties here is that the coin is really immutable. And so in the sense that the coin, the quote-unquote, the coin here cannot be transferred, subdivided, or combined. They can just be destroyed or created. But the good thing is, although the coin is immutable, we still have the properties of coins that is non-immutable, which is you still can subdivide transactions, and you can still split the coins. For example, if you have a coin of $5, right? So you only want to pay $2 to someone else. You just destroy your coin and create two new coins of $2 and $3, and pay these $2 to others, and pay the $3 to yourself. And now everything works. So that's a key design of the blockchain system. So here we only have one worry, really, right? So basically Scrooge himself. Although, so you can see that in this system, Scrooge himself we need to trust, and that's a problem. Although the property of the blockchain can prevent Scrooge for certain kind of malicious behaviors, but Scrooge can just say, "I'm tired today. I'm not going to validate any blockchain transactions," and then the entire system stops, right? So the crucial question here is that can we sort of discrugify the currency and operate without any central trusted party? And this is another central aspect of the Bitcoin design, which is decentralization. And this will be talked by next meeting by Gunnar. And I think that's today's meeting. And also, I want to point out, Bitcoin is not the first cryptocurrency, and maybe will not be the last. So really, there is a very interesting history of cryptocurrencies. And there is an excellent online lecture from a Berkeley blockchain. And it's a super entertaining video, and I would recommend you to see it. And you can view it through the link from the slides. So let's summarize today's talk. So we first introduce crypto hash functions and a few data structures that we can build using these crypto hash functions. And then we talk about a primitive crypto method called digital signatures. And then we talk about one key aspect of the blockchain and the Bitcoins, which is public key as identity. And then I sort of give a very toy design of cryptocurrency and show you what is working, what is not working. So I think that's it for today's lecture, and I'm happy to take any questions.
So these blockchains that you sketched very superficially, at this level, or so far as we reached, can you make any comparison with the log file systems for database recovery? Are there any similarities or any differences that we should be aware of at this point of the discussion?
It's very similar in the sense that how the transaction works on the logs, because you can see that there is a certain point you can commit the transactions, and basically, like from the database point of view, like if you have a log, if you have written a log, this means your transaction is committed. In that sense, it's very similar. But the I think the key difference is here that the validity of the log itself sort of is guaranteed by this crypto method in the blockchain. That's the first. And the second, the way in the blockchain where they store the logs is different. Usually in databases, you just store like wherever storage this database system has. And here, it's really like a distributed storage. And because of they use hash pointers, like you can link this distributed storage together and still verify the validity. And I think the key point here is to have like a stronger security guarantees.
I understand like one difference is in the distributed transaction, any traditional transaction, like there is no like strict order, but here in order to like chain all these blocks, then you have to have like strict order of all the transaction, and this transaction is kind of different from traditional transaction, because traditional is the transaction is defined by logic, but here you decide like which records to put in one block, right?
It's not me, someone first, and I think this is really good. This is a really good question because if you look at the real-world blockchain applications, it's actually more complicated because everything is decentralized, and I think it's actually kind of similar to the concurrent transaction you were mentioning just before, because like essentially sometimes we only know afterwards which transaction is committed, but really I don't think no one can sort of have definite control of, like, if you propose a transaction, this transaction will definitely go through. And in the third lecture, we'll talk about the smart contract and the Ethereum virtual machine, and they have a sort of the bid of the transactions. You actually attach a transaction fee of each single transaction that you propose, and Ethereum calls it gas. And the higher transaction fee you bid, the higher probability your transaction will go through. So they have this sort of mechanism.
So Phil from Microsoft Research has a different answer to Dan's question, so
Okay.
I'll let him
Yeah.
answer.
Okay,
Phil, you
cool.
can go
That's
ahead.
fair.
Hello?
Yeah,
Yes, Phil, you can go ahead.
can I?
Yeah.
Shumo's still talking, at least at my end.
Yeah, that's like a 4-second delay or something. Yes, you can talk.
Can you hear me now?
Yes, we can.
Yeah, okay, good. So, first of all, in answer to Dan's question, the big difference between a database log and I see. Okay, so the big difference between a database log and a blockchain is the blockchain is tamper-proof. You know,
Yes, it makes sense. So there is no
So-
no danger of double spending in the database log. There is no notion of double spending. Nobody worries about double spending.
Don't confuse this with the Bitcoin protocol for distributed blockchain and proof of work. That's a separate concept.
Right.
Yeah, that's right.
As long as you trust the computing entity that controls the database log, you're fine.
Right.
And in fact, I actually agree with Mohan that Shumo, you disagree with at the beginning, that blockchain is the more important concept rather than the proof of work in Bitcoin. And the reason is that most parties to a smart contract will have no problem in having a trusted intermediary generate the blockchain ledger. What they want to know is that all of the transactions recorded in the ledger are non-alterable and can be verified independently by all participants.
Okay, we can talk offline.
Okay, so I think that's all the time we have for the seminar. Stop here, and next week Guna will present the second part.
Thank you.
Thank you.